molasses. And at a little bit higher temperature, 350 degrees or so, it smelled exactly like Jack Daniel's whiskey. People would come by the lab and say, "Boy, you guys must be having fun. What are you doing?" And we were making the stuff of life.
This strange aroma gave Hazen the clue that he too had created organic molecules. Once again, these molecules assembled into tiny membrane-like vesicles. They were behaving much like the molecules extracted from the Murchison meteorite. So Hazen had discovered that it might be possible to create these cell-like membranes close to the deep-sea vents. But other researchers believe that this strange underwater world was capable of providing more than just a cell membrane. They believe that these warm vents were where all life's component parts came together. They claim the Big Birth happened here, at the bottom of a primordial ocean. In order for the Big Birth to occur, scientists believe that certain essential elements had to work together. For example, life needed a container, which came in the form of a membrane. It needed some way to reproduce. Today, this process is achieved through an extraordinary chain of organic molecules, DNA. Life also needed an engine, a chemical process called metabolism that converts fuel into usable energy. According to Dr. Michael Russell at NASA's Jet Propulsion Laboratory, it's metabolism that came first.
Life has a job to do, basically. And I could put it like this. You could have a modern car with an engine and a computer inside, but if you take the computer out, the car will still work. But if you take the engine out and just leave the computer, it won't. The computer is the kind of regulator, but the engine is what's really important. So that's why we think there has to be an engine first, and that engine is metabolism.
Today, the engine of metabolism that powers every living thing is an extremely complex chemical reaction. But intriguingly, Russell thinks we all have traces of the first and simplest metabolic reaction buried within our cells, like living fossils that point to where life began.
We can trace the kind of chemicals in the early Earth and see them even to this day. So, for example, there are iron sulfides in our skin, for example, and that's the little bit of rock that to our mind reminds us where we all come from.
And according to Russell, this is where we come from. Deep-sea vents made largely of iron sulfide. He believes that this and other compounds kick-started metabolism, acting as a catalyst to enable a reaction between hydrogen gas streaming out of the vents and carbon dioxide dissolved in the water. But eventually, this simple reaction evolved to become the complex chemical engine, metabolism.
And eventually, the metabolism required DNA because it did need a regulator, it did need a computer, but to start with, we just needed the engine.
At some point, the metabolic engines acquired some bodywork, a membrane. Russell's theory gives one idea of how a simple chemical reaction could have driven the creation of more and more complex organic molecules, and eventually created the first living cell and all life on the planet. There are still many gaps, but slowly the clues to the origin of life are beginning to emerge. But now a scientist claims that he might be able to put all these clues together using the latest laboratory techniques. He hopes to start life from scratch, something that hasn't happened on this planet for the past 4 billion years. Scientists are striving to answer the great question of how life began. It's a quest that has taken them to the remotest corners of the globe and deep into the inner workings of the cell. But as one group of researchers look back 4 billion years to the Big Birth, another group of scientists is looking to the future. Around 4 billion years after nature first created life, scientists are now able to redesign it. The key to this extraordinary power is their understanding of one extraordinary chain of molecules, DNA. DNA is made up of 4 simple base molecules: adenine, guanine, cytosine, and thymine. The arrangement of these 4 molecules stores the information needed to create life. It's this natural technological innovation that's at the heart of all life on Earth today. And Tom Knight, a computer expert at MIT, wants to reprogram DNA to make new kinds of life.
Fundamentally, there is one technology of life right now. And that technology perhaps was invented, billions of years ago. And all we are doing is changing little bits and pieces of that technology.
For thousands of years, mankind has harnessed nature, rearing livestock and growing crops. Selective breeding has improved yields and created higher quality. But now bioengineers want to take a step further. Instead of just improving nature's original designs, some want to re-engineer life, creating so-called Life 2.0.
We can now think about growing things which are not food. We could think about growing things like nanotechnology level substrates for electronic circuits. I have a student who's looking at placing atoms precisely in patterned arrays on silicon surfaces.
These new life forms might be able to manufacture products for us cheaply and easily.
It's a little bit like going to the store and buying a cell phone, and what comes in the package with the cell phone is not just the cell phone, but also the factory which makes more cell phones.
Re-engineering biology will bring a new era of exciting possibilities, but it will also bring new risks and responsibilities.
And this is the shocking result.
Any new biological factory released into the environment could have unforeseen consequences. A living factory with the ability to reproduce itself could be unstoppable.
This town is in danger.
But for the moment at least, this nightmare scenario is far away because these new organisms are a long way from leaving the lab. As well as hoping to create new forms of life, bioengineering is now giving science a chance to explain the mystery of the Big Birth. Instead of having to attack the problem from the bottom up using basic chemistry, or from the top down by unraveling evolution, scientists can now use the technology of bioengineering to try and put the building blocks of life together themselves and create a living cell. Jack Szostak at the Harvard Medical School is a leader in the field.
We're making the assumption that, okay, someday people will figure out how you make the building blocks you need. What happens if you have the building blocks? How do you put them together? How do you organize them so that they start acting like a cell?
Szostak and his team at the Harvard Medical School have set themselves the task of building a living system in the lab.
Well, we'd like to understand that transition from the chemistry of making molecules to the way that these molecules work together to give us life. So we would like to build a simple living system as a way of trying to understand that transition.
Scientists believe life evolved over millions of years. Szostak is hoping to use the latest bioengineering techniques to do it in considerably less time.
We want to make things go fast as possible. So we're making the building blocks ourselves and putting them together in just the right environment. We would like to get everything going in the time scale of a few years, which is speeding things up by a factor of, say, 100 million.
Szostak hopes to create a working cell from simple building blocks. The only way he can do this is by boiling down a cell to its simplest possible components.
One of the things that's made the origin of life very hard to think about for decades is the fact that all of the life we're used to seeing every day is so complicated.
A big challenge is to create a simpler version of the complex DNA molecule. Szostak believes the answer is RNA. RNA is also made of 4 base molecules, but instead of being wound into a double helix, RNA has only 1 strand.
Now, if you go back to thinking about really early simple cells, you could store some information in just RNA. You don't need to have DNA.
Shostak's goal is to create a simple self-replicating RNA molecule. This, in theory, would eventually form a simple cell capable of duplicating itself. If successful, he may be able to start a process of evolution.
We're interested in the beginnings of life, the transition from chemistry to the beginnings of biological behavior. And to me, the important thing that we have to think of in that transition is the beginning of evolution.
And once evolution can begin, more and more complex cells will be created by the process of natural selection. Eventually, Shostak hopes to be able to evolve a simple, self-supporting, self-replicating biological system. Some might call it life. Shostak's work might one day connect the dots between the building blocks of life and the last common ancestor, and show how inert chemicals can combine to create life. If he succeeds, it will be the crowning moment of over a century of research by some of science's greatest minds. Finally, we might solve the great riddle of how life began on our planet.